talk about a very important area of the machine learning, or more generally statistics, Bayesian statistics, which is Monte Carlo methods. Monte Carlo methods are used in too many various areas, so you should know, you all guys have to know this. And this is actually very interesting because it's a small problem of the machine, the small subset of the problem that any of the machine learning algorithms invent. So it's like tiny toy problem. It's like a sandbox, so you can play. You can take many different approaches to the very to the very simple problem. Which is, so Monte Carlo method is like the definition is, so in machine learning you always consider the probability distributions, right? You always consider probability, and sometimes you cannot deal with the probability distribution analytically. For example, so it's the domain is continuous, and there's some weird distribution. And if you take some function x to y, and if this transfer or if you take this function, then your distribution will be very different. First of all, if this function is linear, there's no problem, because linear transformation is very easy, and you can always do this one analytically. But when it comes to nonlinear function, if x is nonlinear, then you probably not be able to get this distribution on y analytically. So this is a very common problem. You somehow transform this x to y, but if this transformation function is nonlinear, you cannot derive this one analytically. Actually, you can when you can calculate the Jacobian. If you can calculate Jacobian, you can get this one analytically. But if your system contains too many of this nonlinear transformation, then you have to multiply multiple times of Jacobians. Then you have you did have the analytical form of this distribution, but you cannot handle that because it's analytic function, but too complex. So this is just one example why we need to use Monte Carlo methods. There are many other cases, and in this case, what you can probably do is not use entire function, but you make samples. You take some samples. So for this one, you have higher probability near this point, so you take many samples here, but here very rare. And this instead of handling this px function analytically, you take some, let's say, 100 samples from this distribution and transform it, each samples to this y domain, right? And even if this one is nonlinear, it's pretty easy because you can just take this value and your sample will be moved to y space, but there's no difficulty in transformation. So yes, that's basically what Monte Carlo methods are doing. You you approximate the probability distribution, especially the continuous ones, because discrete ones are not difficult. So continuous for the continuous distribution, you take several hundred samples and approximate the distribution with the hundreds of samples. And if you are dealing with the samples, nonlinear transformation or many other complex things can be very easily solved. But there's always trade-off because you cannot drive the exact form, right? Because it's not analytical. So you can only get the approximation. Right? If you transform it and you got this one, and maybe you have some idea that this can be this one, but not exactly. So it's a very nice solved problem, as I said earlier. It's a very simple problem, but interestingly, it's not that very easy. So it's these Monte Carlo methods or Markov Chain Monte Carlo is a fairly big subdomain of the machine learning or statistics. There are many algorithms, and we are going to cover today some of them, very little subset of them, which is rejection sampling, Metropolis-Hastings Algorithm, and Gibbs Sampling. And I originally thought that I could cover the particle filtering, but it might take some time because I heard that you didn't learn the column filtering, right, from this rookie seminar. Right? So it takes some time to explain this particle filtering to you because you only learn the HMM. That one is discrete temporal model, but we need to know the common filtering, which is continuous temporal model. So I'm going to skip this part, and I'm going to explain this, and some of them related to Markov chain, and some of them, others are the related issue with the Markov chain. So basically, so you are given the probability distribution. How can you sample from this? You only have, it's implementation part. So you only have in C or Java or MATLAB or many other programming languages have uniform random function, right? So the random numbers they generate. And some of them, especially MATLAB or Python NumPy, has maybe they have Gaussian random variable, Gaussian random sampler. But if you are given just a random arbitrary distribution, how can you sample from this distribution? That's the problem. That's why there are many Monte Carlo algorithms are there. Do you have any idea how can you sample from random arbitrary distribution? So this is a PDF. It looks like this. Not this. It has to be smooth. And actually, when you are given the discrete distribution, discrete, probability mass function, which is, this is x equals 1, x equals 2, x equals 3, and the sum of these three bars have to be 1, right? If you are given this distribution, how can you implement this sample from this distribution, this mass function? Well, let's say this one is 0.2, 0.5, 0.3. How can you get the sample from this discrete mass function? Only using the uniform random generator. Yes. So what basically we do is sometimes called roulette wheel selection. You develop a roulette and make something like this. And you spin the wheel, and if it stops here, then you take this class 2. Right? So, in fact, as we are just told, you make the cumulative distribution. So, here, 0.2 and 7 and 1. So it's a 0 to 1. So you take the uniform random generator, and if it gives you the 0.1 value, the output of the random was 0.1, then you take x to 1, right? And if it stops, if it gives in between this range, then your output is x equals 2. And if that's range here, then you take the x equals 3. Right? Do you get the idea? 자, 제가 영어 설명해서 좀 잘 못하는데 혹시 질문 있으시죠? 이런 거 많이 구현할 일이 생기잖아요. 그냥 샘플링 저렇게 하는 거죠.
그러면 저 원판에 0.0.4점이다. 그러니까 저 확률이랑 미리 알고 샘플링을 하는 거예요? 아니면
네, 그러니까 우리 항상 PDF는 이미 있어요. PDF가 있는데 거기서 샘플링을 하고 싶어요. PDF도 다 알고 있는데 우리가 그냥 생각하기에는 PDF 알고 있으면 무조건 샘플링 되는 거 아닌가 이렇게 생각을 하지만 막상 이거 구현해보라 그러면은 막막한 걸 느낄 수 있어요. 심지어 가우시안도 만들려고 하면 못 만들 거예요. 가우시안 샘플러는 굉장히 특이한 독특한 트릭이 있어서 만들 수 있는데 유명한 알고리즘이 있는데 근데 뭐 가우시안도 그냥 생처로 유니폼 랜덤만 가지고 만들려고 그러면은 생각하기 쉽지 않아요.
샘플 0수까지 할당해서 랜덤 숫자 샘플 뽑아내는 게 많이 있는 거니까.
네, 그러니까 그게 지금 여기 있는 거죠. 그러니까 그림이 잘 안 보이는데 어쨌거나 중요한 건 이게 CDF라는 거예요. 지금 이렇게 그렸지만 Cumulative Distribution Function이요. 그러니까 마이너스 무한대에서부터 Continuous Distribution 같은 경우에 마이너스 무한대에서부터 이렇게 쭉 적분을 해가면서 쓰이게 되는데 그러니까 뭐냐면은 여기서 보이듯이 0에서 1 사이에 그냥 랜덤을 뽑아가지고 그게 0.2에서 0.7 사이면은 두 번째 클래스, 0.7 이상이면 세 번째 클래스 이런 식으로 샘플링하면 되는 거죠. 이게 디스크리트 분포인 경우. 그게 조금 생각해보면 저렇게 구현할 수 있을 거라는 생각이 들 거예요.
질문이고요.
네, 그러니까 저거 어떻게 구현을 할 수 있냐고.
컨티뉴스?
네, 그러니까 일단 디스크리트에 대해서 여쭤본 거고 이제 컨티뉴스로 넘어가요. 컨티뉴스를 그래서 so if you want to keep in mind this idea, the cumulative distribution idea or relative selection, then if you're given the continuous distribution like this. Example, and also you have unibar, right? And you know that the overall area of this PDF is 1, right? And here's the same. The sum of these bars are 1, right? Here is the same. Instead, it's infinitesimal bars right here, right? So you can imagine that these ones are infinitesimal bars right here, and you use this stacking, just as that figure. Then what you're basically doing is that for sampling for this point, then you need to have this value, right? Stacking from the left. Just like that. And this is a CDF function, right? You are integrating from the minus infinity. And if you go all the way to the positive infinity, then you get 1. It's basically the same as the discrete distribution. Then, okay, you are given some arbitrary distribution, and somehow you manage to get the CDF. And it's not, in general, not true, because you cannot always get the integral. You cannot always calculate the integration, right? Analytically. Sometimes you fail. So getting CDF is one problem. And another thing is that you need to know not just the CDF, you need to know the CDF inverse of the CDF function. So as to, you need to know this, where is this, right? I mean, let's say, well, this area is 0.1, and up to this area is 0.5, 9.7 or something. Then, so you take the uniform random generator, and you got 0.1, let's say. Then you need to, so you know that it's here, but how can you exactly calculate where is this? You need to compute the inverse function of the CDF. 아니요, 그러니까 CDF는 사실 컨티뉴스한 함수인데 저거랑 비교하기 위해서 이렇게 막대로 되는 거고, 그러니까 0.1이 나왔어요. 그럼 0.1이 나온 이 면적이 0.1이 되는 포인트를 찾아야 되잖아요. You need to find the points that when you integrate from minus infinity to some point that sums to 0.1. You need to find this point. So you need to compute the inverse. Because the CDF function starts from 0. If you're thinking that this one is minus infinity, even though it doesn't then it starts from 0. Somehow it increases, and increasing speed gets a little bit slower here, and increase. Finally, at plus infinity, you get 1, right? This is a CDF function. And if you're given point 1 here, then you need to find this point, right? So you need to know that the inverse function. That's another difficult part. Okay. If you are given the discrete probability mass function, it's very easy to get the inverse. But if you're given a continuous function, it's not that easy. It's not to get the CDF because of the integration part, and it's not easy because of the inverse part. So there are two difficulties in general. So how can we resolve this in general? So what you can try is the rejection sampling. This is where rejection sampling comes in. The idea is too simple. So here's the distribution here. You want to sample from this. Instead of sampling from this one, you take dome function Q. So from now on, let's pretend that we can get the sample from at least for Gaussian distribution. I said earlier that you can get the Gaussian sampling. There's a famous algorithm. So you're sampling from this one, but instead of sampling from this one, you assume that this one is normal distribution for some mu sigma. And you take the sampling, so let's say you have samples here, Gaussian samples. But there's a difference between this one and the blue one. So how can we leverage that? Here, the Gaussian density is very high, but the original distribution has very low density. So if you sampled here, then you compare the height. Compare the heights of the original distribution and your proposal distribution. So let's say this point is at 0, and let's say Qx0 over P x0 is 0.7. Then you take this sample with probability 0.7. That's the idea of the rejection sample. So for 70% of the time, at least for this x0 point, you take the samples. And for 30% of the time, you just reject. You just dump the sample. That way you can reduce this gap. You can mention the gap. 다시 한글로 설명하면은 우리가 모르는 샘플을 할 수 없는 파란색 디스트리뷰션이 있을 때 빨간색이 이걸 덮을 수 있는 디스트리뷰션을 하나 정해서 그리고 빨간색에서 우리가 샘플을 할 수 있어요. 샘플링을. 그러면은 일단 샘플링을 해요. 그런데 여기 항상 갭이 있으니까 이 높이 비율만큼 높이 비율이 0.7이었다. 그러면 70% 확률로 이거를 샘플에 껴넣거나 30% 확률로 그냥 버리면 돼요. 그러면은 원래 밀도를 맞출 수 있어요. always have to cover the blue one, which means it is not allowed. This case is not allowed. The blue one has to be below this red distribution. But you know that's impossible because every probability distribution function has to be integrated to 1. And if blue one and red one all integrate to 1, if there's a gap here, then somewhere it has to be like this. So if you are using QX is with a standard distribution, then you cannot cover the whole area. The red one cannot cover a whole blue distribution. So what can you do? Just multiply k times. You are doing sampling, so the exact number is not important. Right? So just make this one larger. I mean, you can, if there's some missing area, something like this, if the distribution was like this, and just multiply the k value like twice, then your distribution will be now something like this, and you can call out this whole area. So this is not exactly the distribution because it cannot be integrated to 1, but there's no problem with this sample.
디스트리뷰션에 대해서는 알고 있다는 거 아니에요?
하나도 계산을 할 수 있죠. X 포인트에 대해서. 근데 샘플링은 못해요. 네. So we
아니 근데
always know
예전에
X, right?
유전 알고리즘 때 룰렛 필 해가지고 샘플링하는 좋은 걸로 쓰면 안 되나? 그냥 저거 기능을 잘라서 디스크리트를 생각해서.
그게 지금 하고 있는 거. 그게 이거 하는 거예요.
그거.
네. 근데 기능을 하면
기능을 해서 내가 그냥 유니폼 랜덤하게 숫자를 뽑은 다음에 그 기능에 대해서 할당을 하는 거지.
네네. 그러니까 맵핑 하면 돼요. 그러니까 히스토그램으로 이거 저기 근사해서 하셔도 되는데 그거는 뭐 이제 다른 알고리즘이 있겠죠. 근데 리젝션 샘플링은 일단
지금 그런 거 리젝션 예전에 봤는데 저 갭이 저 비율보다 작은 거 같은 거. 그러니까 저기 저렇게 갭이 커지면은 그냥 리젝션이 되는 거.
그렇죠.
아니 보상을 해서 내뱉는다는 거.
제가 설명 드릴게요. So I mean, is everybody following to this point? Do you all have idea of the rejection sampling? Then what is the problem of the rejection sampling? Why do we develop another algorithms? Because sometimes this area is too big, too large. So if you want to sample from this blue distribution, but if you take samples from red one, you almost always dump it because this area is too large, right? Let's say this is the one you are sampling from, and your rejection ratio would be this big, right? And it's not an efficient algorithm. So if you want to get 100 samples, and you need to actually sample like 10,000 times. That's a problem. It's right. Since I mean, Monte Carlo methods are very interesting because it's very related to the computational issues. Right? In theory, you don't have to care about Monte Carlo methods or Markov Chain Monte Carlo. It's all related to computational problem. So the only objective of the Monte Carlo method is computationally not expensive. That's the objective. So this one is not a very good algorithm. In fact, this one is 1D problem, right? But if you want to sample from the 100 dimensions, let's say what we are dumping here is like 70%. Or let's say it's just a 1%. 10%. So if you're dealing with one-dimensional probability distribution, it's quite good because 90% of the time you get your samples. But if you do this for 100 dimensions, then you only keep the 90% of the time. So it's like 0.9 to the 100. So it's very, very small value, right? So that's another example of cursor dimensional. If you have 100 dimensions probability distribution, you cannot do this because your dumping area will be, dumping volume will be larger and larger. It gets larger and larger. So you can use this distribution. You can use this method. So that's why Markov Chain Monte Carlo methods are needed. Do you have questions so far?
엔지니어링으로 생각을 해보면 px 나누기 qx 그러니까 값이 1보다 작아야 하기 때문에 프로포절이 더 커야 된다고 했잖아요. 근데 만약 1.5가 나왔어요. 그 비율이 1만큼을 샘플링하고 0.5 한 번 더 샘플링해서 이제 50% 확률로 더 추가하는 방식으로 하면 그 높이가 더 큰 부분도 처리를 할 수는 있잖아요. 엔지니어링으로 생각하면.
그렇죠. 뭐 그런 것도 한 방법이 될 수 있죠. 네. 다 이거 이제 뭐 예를 들면 실제 디스트리뷰션이랑 얼마나 샘플링이 차이가 나오는지 뭐 그런 메저들을 다 비교를 해봤을 때 항상 다 장단점이 있죠. 그런 방법도 쓸 수 있어요. 예를 들면 보통 1을 넘어가면 임포턴스 샘플링 같은 걸 하는데, 그러니까 말한 것처럼 1.5라는 값을 그냥 샘플이 갖고 있는 거예요. 그래서 나중에 접근할 때 우리가 항상 몬테카를로 메소드 결과적으로는 몬테카를로 메소드는 지금 일단 분포에서 샘플링 해가지고 뭘 하는 거지만 마지막으로는 익스펙테이션 계산을 하거든요. 우리가 필요한 건 익스펙테이션. 예를 들면 에러 계산하고 싶어요. 데이터에 대해서 익스펙테이션 취하잖아요. 익스펙테이션 취할 때 접근하는 거니까 임포턴스 그냥 그대로 갖고 있으면서 하면 돼요. 근데 임포턴스 샘플링도 문제가 생길 때가 있어요. 그래서 여기서 임포턴스 리샘플링을 하는 이유가 문제가 생길 때예요. 예를 들면 어떤 문제가 생기냐면 임포턴스 이만한 녀석이 하나 생기고 이만한 어떤 거 있어. 이렇게 생길 때가 있어요. 그럴 때 이거를 이제 쪼개가지고 여러 개 만들어주고 그런 작업이 필요해요. 그러니까 되게 지금 보면 MCMC나 MC 메소드들이 되게 웃겨요. 보면 이거 왜 하나 싶어요. 약간 웃긴 문제들 풀고 있어요. 그 머신러닝이 필요하면은 막 이런 거 막 쪼개줘야 되고, 근데 다 컴퓨테이셔널 이슈가 있어가지고 그런 걸 다. Explaining than I thought. So we are going to cover the MCMC now. So for high dimensional data, rejection sampling is not a proper method. And another drawback is it's hard to make the envelope distribution, which is coverage distribution. You need to make sure that the distribution covers on all the domains. That's kind of hard to find. So that's the two drawbacks of the rejection sampling. So that's why we need Markov Chain Monte Carlo methods. And this is another trick. So it is a Monte Carlo method, but you use Markov chain. So the Markov chain is not necessary for what we want to do. But this is also a technical trick. So do you know what the Markov chain is? Do you know the Markov property? Markov assumption? How many of you haven't heard about the Markov assumption? Okay, Markov assumption is pretty simple. So you have sequence of random variables, x1, x2, x3, x4. These are not IID random variables. It's just a random variable, sequence of random variables, and there's a dependency. So x4 is related to x3. There could be many other different dependencies. And if you want to decompose this joint distribution, what at least you can do is something like this. x1, p of x3, x1, x2. Let's remove that. Right? But using Markov assumption, you can delete this one. Markov assumption is that only the neighboring, actually the very last one can make effect on the current one. x1 cannot affect x3. The very neighbor, the very latest random variable can only make some effect on x3. So there's no dependency between x1 and x3. Right? That's the Markov assumption. So using Markov assumption, actually, I mean, you've already learned the hidden Markov model. I mean, you should know the Markov assumption, right? Hidden Markov model looks like this, right? And these are hidden nodes, right? And the hidden Markov model is that hidden nodes are assumed as a assumed to have Markov property. So this one does not give any effect on this one. Right? Only this one is related to this one. So if this one is given, you don't have to care about this x1, right? x1, x2, x3. If you want to know the random variable of x3, then you don't need to care about x1. If you know what the x2 is, so that's why we can delete the x1. So I've already shown here Markov chain. For Markov chain, you can draw like something like this. It's chain. And there are several states. So if you moved on to this one, and if you are trying to move from this to this, then you don't need to care about this one. That's the Markov chain. And why do we care about Markov chain? We are just doing Monte Carlo. So the Markov chain is a very interesting trick. So let's just assume that we are dealing with the discrete distribution, discrete math function, S function, for simplicity. So we have 4 different candidates. I mean, you are dealing with a single discrete random variable, but you can have 4 different values, 4 different states. So basically what what we want from Monte Carlo is that we want to have samples of this distribution, this distribution, right? But instead, we want to make a Markov chain. It's weird enough. Why do we need to care about the transition? So, there are many connections, right? So the reason why we create this Markov chain is that we cannot directly sample from this one. So it will be very convenient if there's some kind of this Markov chain that you just start from here. You're at X4 position, and you just wander around according to the Markov chain. So, for example, for 70% of time you go to the X3 node, and for 0.1 you stays at the current state, and in 0.5 something, in 0.5. As there are 4 states, these has to be summed to 1. Anyways, so you start from this node and you just wander around, and hopefully your history of visiting nodes have the same distribution as the original. That's what MCMC wants to do. So instead of directly sampling from this PX, we use some weird technique, which is basically just transition probability, the transition probabilities between the 4 states. Using these 4 states, you just start from random nodes, random picked nodes, and wander around according to this transition probability. And if you wander around, let's say you start from X4, and this was your history, right? Something like that. Then you have Monte Carlo samples. Okay. Your history becomes your PX samples. That's the idea of MCMC. But how can these two be the same distribution? That's the next question. So you need to make this transition probability such that if you wander around according to the transition probability, then you get the same distribution as the original. That's what we need to solve in Markov Chain Monte Carlo. 한국말로 다시 말씀을 드리면은, 그러니까 우리 PX에서 뽑고 싶은데 PX에서도 어쨌거나 지금 뽑는 게 어렵다는 거를 이 앞에 부분에서 계속 설명을 드렸잖아요. PX를 우리가 다 알고 있는데도 샘플링하는 거는 또 다른 문제라서 어려워요. 그래서 그거를 리젝션 샘플링에서는 어쨌거나 좀 이렇게 더 크게 씌워가지고 여기 필요 없는 부분 날려버리자 이런 식으로 해결을 볼 거고, 여기서는 완전 다른 방법을 써서 조금 비직관적인데, 그래서 우리가 트랜지션 이런 거 할 필요 없어요 사실. Because we are sampling from the IID distribution, so IID samples. You don't need to care about this transition. You don't need to care about the Markov property, because for IID you don't have connection between this random variable because they are independent distributions. So there's no dependency. There's not even the Markov dependency. Origin. But why? 그런데 이제 Markov chain은 이게 디펜던트잖아요. 그러니까 여러분들이 알고 있는 이 X랑 다른 완전 다른 그냥 쓸모없는 거 갑자기 그냥 나온 녀석이에요. 그냥 테크닉. 그런데 이걸 이용해서 이렇게 막 움직이면은 요거랑 똑같은 분포로 나오도록 이 트랜지션을 정리를 하고 싶은 거예요. 그게 MCMC에서 하고자 하는 거고. 그래서 그거를 굉장히 잘한 게 이제 메트로폴리스 헤스팅스 알고리즘. 그리고 깁스 샘플링. So it's kind of hard to get. Maybe we'll get better if I explain about the Metropolis-Hastings. So what would be the condition that you were wondering? Sorry for my pronunciation. So you just wander around. You were wondering. History has to be same. Has to be the same with the original distribution. What would be the condition for that? So MCMC, you are designing the transition probability, transition matrix. How can you design the transition matrix? So let's do this. These are the same. So let's say this is a transition matrix T. T is a 4x4 matrix. And because there are 4 states, and let's say X is X. Sorry. And for transition probability, it's actually elements of the transition matrix is like this. So the first row, first column has probability of x1 from x1. So this one, x1 from x1 is on the 1.1, and for 1,2, first row, second column, its elements represent the probability of going from x2 to the x1. So this one, and etc. So basically, if you are at some state, and if you want to predict the next state, then you can just multiply P with T, the matrix multiplication. Let's give you some example. Because you don't know what the Markov chains are. Let me give you a very simple one to save some time. So this one is x1, this one is x2 state. And let's say this one is 3, this one has to be 7, and this one 0.5, 0.5. And your transition matrix will be, so 0.3 and 2 to 1 are at x1, then your probability matrix P will be 1, 0. And if you multiply it here, then what you get is very simple. 0.3 of being here, 0.7 for being here. And if you do this simulation again, then you can just multiply it once again. And you can do the same calculation. This one is actually marginalization. The multiplication of this matrix is actually marginalization. Because there's a summation, right? This one is drain distribution. Multiply these two up will give you a drain distribution, and summation will marginalize. Okay, so what I want to tell you here is that if you just multiply these matrices again and again, then you will wander around. And important part is designing the T matrix, right? I keep saying that we need to design T matrix to make these samples and this distribution to be the same one. So, but in CMC, I mean Metropolis-Hastings solution is actually that what would be the condition of the T? It's very simple. P of xi, P of xj, xi has to be the same as xj, pxi given xj. Transition. It's actually probability, but the convention is this. If this condition is satisfied, your Markov chain will converge to the original distribution. That's very important theorem, which is called detailed balance condition. If your Markov chain were transition probability of your Markov chain satisfy this condition for all I in J, for all ij, it means the detailed balance condition is satisfied, then your Markov chain will be converged to your original distribution, Px. And this condition is a sufficient condition, but not necessary. So if the detailed balance condition is satisfied, it is sufficient for the Markov chain converges to the original distribution, but it is not necessary. There's a little bit smaller set of conditions. But the reason why we consider the larger set of the condition is that this one is easier. your probabilities here, let's say it's 0.7 and it's 0.2, 0.1. That's the current state. Then, if you take one-step transition, so transition from here to here, this one is x1, x2, x3. Then amount of going from x1 to x2 has to be the same from amount of going from x2 to x1. That's what this condition is saying. You have 70% of chance of being x1 state, and for x1 state you have some percent of chance of going from x1 to x2. And that's the same for x2 state, for going from x2 to x1, etc. And that has to be the same. Not just a simple transition probability, but with your condition of the current state. So if you are if you are giving and receiving the same amount, then you will be in the steady state. So probability density is not going to be changed. So this is actually the condition for the steady state. That the steady state is actually the original distribution we want to get. We can prove this one. I'll just skip that. So let's for now just believe that the detailed balance condition is a sufficient condition for the convergence and converge it to the PX. So now what we need to do is make the transition probability to satisfy this detailed balance condition for all I and j, for any arbitrary distribution. That's what we want to develop. And that is Metropolis-Hastings Algorithm, which is quite intuitive. So, let's say you are here. Currently you are here. And we need to transit to the another state, another value. And we don't know exactly what this one is. Let's say that's a Gaussian distribution, something like this. Or any other thing can happen. You can make the uniform distribution. Same as the rejection sampling, you need to have some distribution that you can actually sample from. I mean, you can make the algorithm to get the sample. So for a uniform or Gaussian distribution, you can get the samples. So we don't know what t is yet, but let's just try it with some silly distribution, like something like this uniform random or Gaussian random. And just transit from this state to another state. Or maybe you sample from distribution, then you get this one. say. But that's obviously wrong because we did not consider the detailed balance condition. So we need to compensate it and leverage the difference. So basically you replace this one with two parts. This one is and you have I've rewritten the detailed balance condition, so this term is T. I just decompose it. So the Q part is the proposal part. I use the Gaussian distribution or uniform distribution, any distribution you can sample from. You propose, even though it's wrong, but you propose and compensate the difference with these R function. That's what we are going to do. What will be this ratio? We need to compute these two, but we only have one equation, so I'll just write in the ratio. So if you find right, this one will be 한국말로 바꿔서 설명을 하면, 그래서 MCMC는 결국에 몬테카르로 샘플을 구하기 위한 어떤 특수한 트릭 중 하나로 마르코프 체인을 이용하는 건데, 마르코프 체인이 이런 디테일드 밸런스 컨디션이란 이 녀석을 만족하는 트랜지션 매트릭스를 찾으면 우리가 어느 스테이트에서 출발하든 PX로 수렴을 하게 돼 있어요. PX 디스트리뷰션. 그러면은 이 문제가 리듀스돼서 T만 찾으면 되는데, 그걸 찾기 위해서 지금 이렇게 뭔가 우리가 샘플링을 할 수 있는 디스트리뷰션이랑 그걸 이게 잘못됐으니까 맞춰주기 위한 두 개를 나눠서 지금 R을 구하려고 합니다. R을 구하면 우리가 T를 다 구한 거고, 그러면은 샘플링을 할 수 있게 돼요. 마코프 체인을 따라가기만 하면. So, are you okay with this equation? This sounds great, right? So, as I told you earlier, you have two unknown values, but you only have one equation, so it's kind of open in 1 degree of freedom. So let's say you computed this one. if you computed this one, or actually if your proposed transition matrix was in fact the correct one, this has to be 1, right? But in general, you choose just a silly distribution, so it cannot be 1. Some value near 1, right? Let's say you computed this value, and this one came out, turns out it's 1.5. Then what you can do, you can make something like this, or maybe, what else? 0.75. 네, 3대 2네요. 그러면은 그죠? 0.75대 0.5. 네. Yeah, you can choose something like this. You have 1 degree of freedom. So what value we should choose? What can be the best one? It is. So what we desire is this one. We want this one also probability distribution. So we don't want 3, 2. We want this value has to be in this range, from 0 to 1. And this one also satisfies this property, right? And is this sufficient? There can be many others, right? Even satisfying this distribution, right? So the best thing is that make at least one of these to 1. Because for 75% of the time, you will make the transition, but for 25% of the time, you don't make the transition. I didn't mention that, but another important property of the Markov chain is that it has to be dynamic. It's called mixing. So you need to get a better mixing for your Markov chain is good. So for better mixing, your transition matrix has to be very dynamic. Not dynamic means that your Markov chain is not like this. Like 90% of the time you stays in your state. That's not a very good idea for a dynamic system, right? Your sample has to move very fast from state to another state. So what you can do is that make one of them 1, and what you can do is set this one to 1/1.5. Right? How can you make that? In fact, if you take just describe this function. So that what this means is that I just write this the same time again. It's a mean of 1 and this value. So if this one is larger than 1, then you take 1. And if this one is smaller than 1, you throw the 1 away, then just take this one. So for now is 1.5. So your result will be 1. So it's here, right? And if you calculate this one, not this one, this one, then you will get this value. Taking this. As you can see here, for this R, this term is split. If you calculate that, so it's 1 over 1.5 here for this R. So it's smaller than 1, so you can just take 1 over 1.5. To summarize the Metropolis-Hastings algorithm, is you compute this value first. R. First, you compute this value, and second, for probability R, you take the transition from xi to xj. For probability of 1 minus R, you just stay. That will be your next x. 그래서 실제로 이렇게 하는 거예요. 그냥 이런 분포가 있어요. 처음에 그냥 어딘지 잘 모르니까 x는 0에서 출발해요. x는 0에서 출발해서 우선 우리의 q 디스트리뷰션이 있으니까 q 디스트리뷰션으로 뽑아요. 여기가 중심이고 뭐 베리언스 뭐 일자리인 예를 들면 가우시안을 선택했어. 여기서 샘플을 하나 뽑아요. 그러면은 그 샘플로 갈 거냐 말 거냐를 저 R이 결정을 해주는 거죠. 그래서 뭐 저기 Q든 P든 다 계산할 수 있어요. 왜냐면은 계속 강조를 하지만 우리가 PX를 모르는 게 아니에요. PX를 알고 있고 모든 포인트에서 이베리에이션도 다 할 수 있어요. 그러니까 이 포인트에서 덴시티가 얼마고 이 포인트에서 이 생긴 것도 어떻게 생긴지 다 아는데 샘플링을 못할 뿐이에요. 그래서 P도 다 지금 이 포인트랑 이 포인트 둘 다 P도 계산할 수 있고 트랜지션 프로버빌리티 우리가 정의했기 때문에 계산할 수 있어요. 여기 있을 때 여기로 갈 확률 요 값이겠죠. 요 P. 반대로 여기에 놨을 때 이렇게 생기니까 요 값이겠죠. 가우시안은 대칭이어서 저 두 값이 같아서 상쇄되는데 뭐 여러분들이 비대칭 비대칭 디스트리뷰션 이런 거를 쓰고 싶다면 이런 걸 써도 돼요. 그러면 상세는 안 되겠지만 유니폼도 상세되고 지금 대칭이면 상세가 다 되는데 Q 텀은 상세가 되는데 어쨌건 그런 식으로 하는 거예요. 저거 4개를 다 계산을 할 수 있으니까 저 R 값을 계산할 수 있고 그러면 이거 이제 옮겨 다니는 게 중요한 문제가 없죠. 그래서 막 옮겨 다니면은 그 샘플들이 여러분의 샘플이 되는 거예요. 그걸 뽑고 싶은 디스트리뷰션 샘플. 왜 그러냐면 이 메트로폴리스-헤스팅스 알고리즘은 디테일드 밸런스 컨디션 만족시키는 거고 디테일드 밸런스 컨디션 만족되면 마커브 체인 막 돌아다니면은 결국 PX가 수렴한다는 게 제가 증명한 증거는 참 쉽게 할 수 있어요. 성공할 수 있어요. 그러니까 MCMC가 돌아가는 거를 보신 적이 없다면 I'm going to show you just a short demo. It's actually a little bit different algorithm. So this one is the original true distribution, and you want to sample from this distribution. And I'm showing here this Metropolis-Hastings algorithm with the Gaussian proposal distribution. So so you start from just random arbitrary points, but you propose this new state, and you can stay here or you can go there. But as you can see here, if your new point have a larger density, I mean, let's pretend this can be cancelled because of it's a symmetric distribution. Then if the new state has larger density, you have one probability to go to the new point. So you start from here and moving around. If your new proposal goes too far away, then you may not go there and you stay on your ends, where your ends. You keep doing this again and again. And as you can see, it doesn't have a very good performance because there is a whole other density area, but it failed to go from here to there. So it failed. But if you try multiple times, some trial you will get here. So Metropolis-Hastings is not always good, but it's very good. But that's because I started from here. But if you have any information about the probability distribution, where it is concentrated, or maybe you can take the average point if you start from here, then you may have more chance to go through this one. Anyway, so I can show you another algorithm, which is the Hamiltonian Monte Carlo algorithm, which basically gives him velocity. I mean, it's Hamiltonian dynamic simulation. It's a kind of complicated idea, but basically you can move around very fast, so you get a better sample. There are many different kind of machines algorithms. Yes. So this is the comparison. So you sample from this one, and I just did the current density estimations. So these points are representing the true distribution as this one, approximately. And this one is a little bit better because we have density here and here. As you know, earlier it cannot go from here to there. Okay. So I finished the Metropolis algorithm, Metropolis-Hastings algorithm, and the Gibbs sampling is much easier. So I can end this in 15 minutes. So, Metropolis-Hastings algorithm has another issue. It's actually, we cannot resolve the Kursov dimensionality issue. If you're dealing with the high dimensional data, high dimensional probability density, you cannot actually use the Metropolis-Hastings algorithm. It does have a similar drawback because you are also using the proposal distribution, and proposal distribution also fails in Metropolis-Hastings algorithm, as I showed you earlier. It's just like rejection sampling. If you have a higher dimension, then almost always you will get a very small value of R because density is concentrated on very small volume in high dimension. So if you go to almost all directions, then you get a smaller density value, so which means that R is very small in almost all directions, except very tiny area of direction that increases the density. So it is not appropriate for high dimensional data as well. So for high dimensional data, you have to do Gibbs sampling. I think this one is the only option for high dimensional data, as far as I know. But you can combine Gibbs sampling with the Metropolis-Hastings or Hamiltonian Monte Carlo. So Gibbs sampling is very similar. So if you're at x, sorry for the poor notations, but let's say this is the teeth step sample. If you do the Markov chain wandering around, then you'll have these samples. Sorry, I just changed the notation. Yeah, something like this. Then, how do you transit? So for Gibbs sampling, you do transit single dimension at a step. So this x is now a high dimension, right? It's a vector. So if you're using Metropolis-Hastings algorithm, you maybe take Gaussian distribution, uncorrelated Gaussian distribution, and maybe you go this direction. And separate from here, accept or reject polynomial. Something like this happens. In Gibbs sampling, if you're here, then you do this or in coordinate manner, one dimension at a time. You always have to follow this direction or this direction. But you need to be careful. This is not a single step. These two combines to a single step. Are you following what I'm saying? So take this to get a new sample, and this to get a new sample. Your one step is actually consists of these two small steps. So what's good about it? This algorithm is good because you only consider one dimension. Even if you are in 100-dimension space, you take one-dimensional step. So to get from here to here, you just sample from single dimension, which is in fact so you are at xt, and you want to sample a dew point, and what you need to do is compute the conditional distribution. Because you know the joint distribution, I mean, you are sampling from this one. This is a joint distribution of the. Sorry, this one is a notation for the dimensions, and this one is a notation for the samples. So P of x is actually P of x1, x2, x3 to the xd dimension. So d-dimensional probability density function. And if you so what you need to do in Gibbs sampling is that, except for this ith dimension, you are given all the dimensions except that dimension, and you sample from this conditional distribution. And this one is pretty easy because this one is one-dimensional density function. It should be very easy. But if you have trouble with this distribution, you need to do the Metropolis-Hastings. But most of the case, you don't design that much complex strength distribution. For example, if you are in RBM, it's just a binomial distribution. So it's pretty binomial or Gaussian distribution. So it's pretty easy to sample one dimension. So you take this again and again. So you start from here and make other, let's say it's a three-dimensional space, and make other 99 features the same, and just sample the first dimension, and you have moved to this one, and then set another 99 and move this way. Sample around, and you get to this point after 100 sequential sampling. And this is your new sample, not the intermediate ones, just this one. And important thing is, if you use Gibbs sampling, your R is always 1. That's why Gibbs sampling is really a good algorithm. You don't reject. You always accept, because R is 1, always. I was planning to prove that, but it's kind of maybe some time. So I should stop here. But it's the basic idea is very easy, because if you remind the detailed balance condition for this notation, some specific x prime. Has to be the same. Where's this one? Transition. I'm not going to go into the details, but I will give you an idea why the Gibbs sampling has an R of 1. Reason is that the detailed balance condition is this one, right? And what you're setting here is that this one to the conditional distribution, right? Pxt plus multiplied by conditional distribution of this. This one is, this one here is something like this, right? If you multiply these two, then you'll get the direct distribution, right? And you'll have the same from the bottom, right? So it's always the same, because you are using the conditional distribution. That's, there's some, 이렇게 그냥 다 써버리면 좀 문제가 있는데, 이렇게 스텝을 통해서 갔을 때 지금 이렇게 되는 걸 써야 되는데, 그래서 지금 이 수식 자체가 딱 맞는 거 아닌데, 그냥 아이디어만 드린 거예요. 컨디셔널 디스트리뷰션이기 때문에 여기에서 이거 컨디셔널과 여기서 이거 컨디셔널과 조인트가 같아요. 조인트가 항상 같기 때문에 저기 R이 항상 1일 수가 있는 거예요. That was a Gibbs sampling. We're going to use Gibbs sampling a lot. Normally you don't use Metropolis-Hastings, but you are going to use Gibbs sampling a lot. So you should know that. And it's much easier than Metropolis-Hastings. unless you use Metropolis-Hastings for this one. And lastly, I want to mention for 3 minutes that MCMC is a great algorithm, but you need to be careful in practical use. First one is the burn-in time. I show you in MATLAB code, MATLAB demo. Let's say your distribution is here, and you start from here. Then, if you do the Metropolis-Hastings algorithm, it takes very long time to be here, which actually matters. At this point, it doesn't matter, right? But if you take samples here, then your distribution will be something like this. It's not the distribution you want. So burn-in time is that you need to dump several hundreds of data from the initial point. It takes some time to get converged to your desired distribution. So that's burn-in time. So if you implement MH or Gibbs Sampling, any other MCMC algorithms, you need to use the you need to bear in mind the burn-in time. You need to dump some initial several hundred samples. And another thing is that as MCMC is a Markov chain, your neighboring samples are correlated. You are not sampling something like this, right? But what your original one is IID samples, right? IID samples is something like this. Just move. Your previous step doesn't matter anyway for the next step because it's IID. But what you are doing here is MCMC, which is Markov chain. So your previous state matters because if you are at this point, you take Gaussian distribution, and your point is somewhere near here, not here. So it's not IID, it's correlated. And this for one step. So you want to remove this dependency. So what you are doing, what you should do is thin, which is basically, even though you are moving from x1, x1, x2, x3, x2, you don't. You just throw away this part. You are taking samples every 5 steps, something like that. So if you want to get 100 samples, then you need to do 500 simulations and take samples every 5 steps. That way you can, this one and this one, it's related but not that much. So if you're taking every 5 steps, you can remove the dependency issues. And that's the same part. So if you want to make sure your MCMC algorithm is doing all right, what you need to do is correlation analysis, which is you plot the correlation here and the step difference here. So if you have one step difference, you have a very large correlation. But as the t difference is 1, 2, 3 gets larger, then your correlation value will be exponentially decay. So if it doesn't, if it keeps like this, then you need to throw away more samples to make a little dependency. So sometimes you need to plot this kind of correlation graph. And that's it for my presentation. I didn't actually cover many things. I should have mentioned the ergodic Markov chain. But you can read it from Wikipedia. I didn't cover the ergodic Markov chain, and I didn't prove the detailed balance condition, and I didn't prove exactly why Gibbs sampling has a value R equals 1. So you can prove or find it by yourself.